Hey! All right, guys, we're back at it. I hope you all had a great weekend. Yeah, Midshipman Barry, what you got?
Hey, sir, I just wanted to say that that's a pretty sweet mustache.
Thanks. You got a pretty sweet one going on yourself, man. It's tight. All right, so what are we doing today? We've got chapter 30.6. We're going to be talking about RL circuits. I want to remind you about one aspect of inductors, right? We said that when there was a changing current, right, through an inductor, then there would be a self-induced EMF, right? That's self-inductance through that inductor that was given by this expression. That self-induced EMF is the negative times the inductance times the rate of change of current. This is going to come into play when we're calculating our RL circuit. Okay, so the way we have an RL circuit set up here, I've got my battery, I've got a switch here that's got two terminals, A and B. I've got my resistance with resistor R, and I've got my inductance with inductance L. Now, when we move the switch to position A, what happens is a current begins to flow. A current is driven by the battery through the resistor and then through the inductor. Now remember, the current doesn't just become large all of a sudden, right? It takes some time. And as that current is growing, right, in this case we have a rising current, as that current is growing, our inductor is going to be having a self-induced EMF that's opposing that change. All right, what we're going to do to calculate this is we're going to apply a loop rule, Kirchhoff's voltage law, okay? We know for the battery we've got the plus and the minus side. All right, for our current, remember for our rules we said plus where current goes in, minus where current comes out. And for our inductor, since the rising current is going to be opposed by that inductor, it's going to have a self-inductance arrow that points, in that direction. So similar to our battery's EMF arrow points towards the positive, right? This is pointing towards positive. So we put our plus and our minus signs there. Okay, then we just do our loop rule, right? So you pick a point to start. I'm going to pick right here. I go across my battery, I circle the second sign. I go across the resistor, circle my second sign, go across the inductor, circle my second sign, and then I'm back to where I began. Then I can write my voltage law based on those signs. So I would have a positive EMF minus the voltage across the resistor, which is IR, minus the voltage across the inductor, which is that self-induced EMF. Okay, and that's L di dt. And then I get back around to where I began. We set that equal to 0. This is a differential equation with respect to current. Okay, and the solution to this differential equation is that current is going to be equal to the EMF over R times 1 minus the exponential function raised to the negative t R over L. All right? This is the expression for how the current changes with time when we have a rising current through an RL circuit. Okay, one thing I want to point out here is that this term, right, is related to our time constant. On your equation sheet, this expression is written as negative t over tau sub L, where tau sub L is the inductive time constant. That inductive time constant is the inductance over the resistance. Okay, I like to just write it out because remember this is a 1 over the time constant. So when we put this in the equation, we remember to invert that. Okay, it has to be inverted when we write it out fully. Okay, remember we first introduced a time constant in RC circuit. We had the capacitive time constant. This is an inductive time constant. And the time constant is just a measure of time where a certain percentage of whatever we're measuring, in this case current, will be met over a period of time. If we were to plot the current as a function of time, it would start off low and then asymptotically rise up to our maximum current. And the maximum current, right? If we examine this expression at some long time later, right? The exponential function raised to negative infinity, right? This becomes 0, right? Which means that the maximum current is just EMF over R. That's I max. Which makes sense because that's just our function of Ohm's law, right? Where Ohm's law states that EMF is equal to IR. So that's what we would expect due to Ohm's law. All right, so the next thing I want to talk about is, how this inductor behaves initially and after a very long time. Remember, if we switch the switch to terminal A, initially there's very little current, and that current has to rise over time, and this inductor is going to be opposing that change. So initially, it's acting as a resistance to that change in current. As time goes by, right, that current wins out over the self-induced EMF from the inductor, and eventually that inductor just behaves like a straight wire. Okay, so now let's think this has been, this circuit has been going for a very long time in position A. So the inductor is just acting like a wire, current is just flowing through it. I just have EMF and R. That's all I've got essentially after a very long time in position A. So then what I do is I switch to position B. Okay, so we had a current running through this circuit as if this wasn't even there, and then I switch to B. Now that current has to go away, right? It has to decay over time. And again, that inductor wants to oppose that change. The current was running this way, but now it's decaying. So now we have a decaying current. This current is going clockwise, but it's getting smaller and smaller. That EMF wants to oppose that change in current. So it induces its self-induced EMF in that direction, right down, in order to try to keep that current large. All right, we would do the same. We could do a loop rule. We would do the same thing. You get an EMF. You get the self-induced EMF, and you get the IR over here. And when we do that, and we do the differential equation, what we end up with an expression for the decaying current is as follows. We get the current is equal to some initial current. Okay, it could be maximum current. It could be whatever the initial current is. We're just going to call it I naught. Okay, so some initial current times the exponential function raised to the negative t R over L. That is our expression for a decaying current. I want you to remember this initial current could be anything, but if we were in position A for a very long time, it would be the maximum current, and we know that a maximum current, I max, is going to be EMF over R as a function of Ohm's law. Questions? All right. We'll do some sample problems here next. Hope you have a great day.